Hello and welcome to this video on determining whether a linear transformation has an inverse. I should say an inverse that is also a transformation or a function, right? Remember, a transformation is like a function. You have every value or every element of the domain being assigned to exactly one element of the codomain. All right, so we're determining whether a linear transformation has an inverse transformation, right? An inverse that is also a transformation. And I'll point that out in some pages coming up. All right, so I'll start off by defining what is, an inverse linear transformation. And then I'll go over a few pages where I talk about what I just said a second ago about how, every transformation has an inverse, but not every inverse is a transformation or a function. Right. So we'll go over and talk about, I'll talk about the conditions under which a transformation T will have an inverse that is also a transformation, right? In other words, T is invertible. I'll define what it means for T to be invertible. And then discuss the relationship between an invertible transformation and its standard matrix. And then finally, go over several examples where I'm given function transformations, linear transformations, and asked to find their inverses if they exist, if the inverse is a transformation also. And one final example at the end where I do the same thing for a composition of transformations. Right? Find the inverse of a composition. So a lot of stuff going on here. Let's get into it. All right. So first, I define, what do I mean by inverse linear transformation? So suppose we're given a linear transformation T. All right. So this satisfies the additivity. Every time I say linear, right, it means satisfies the additivity and homogeneity properties from vector space U to vector space V. And this particular transformation maps a vector from vector space U, a vector U, to V, meaning that V is the image of U under T, or V equals T of U. Right. All an inverse does is reverse the mapping. So like if U maps to V in T here, under T, then under the inverse, V will map right back to U. An input of V will map to an output of U. So the inverse linear transformation, denoted by, T with a little -1 above it, that's T inverse or inverse of T. And like I said, it just reverses the mapping. So T was a transformation from U to V. T inverse will be a transformation from V to U. And what's going to happen is it's going to map that V right back to the U it started from under transformation T. I got a little picture of what I'm talking about right here. So suppose these circles, this circle represents the vector space U. This circle represents the vector space V. Suppose I take a vector from U called, vector U here, and then under T, right, this arrow, U maps to vector, say, V in the codomain. Then in the inverse, right, under T inverse, the arrow going the other way, the domain is V, the domain and codomain switch, as you've seen, right, they flip. That same vector V as an input under T inverse would map right back to U. It just reverses you back to where you came from, right? Okay. So, I want to point out something to be very careful of on the next few pages. And you probably saw this in an algebra class at some point, pre-algebra or pre-calculus. every transformation, right, every function, right, remember, I'll recap the definition of transformation. A transformation is a rule, right, that maps every value of the domain, every element of the domain, to exactly one element of the codomain, right, and that makes up the range, right, all those elements that get mapped to. So every function, every transformation has an inverse. I mean, you can always just reverse the mapping. That's not a problem. The question is, will the inverse also be a function, right? Will the inverse also satisfy the definition of a transformation? So every transformation has an inverse, but not every inverse is a transformation. All right, let me show you some pictures, and then we'll talk about the conditions under which the inverse mapping, the reverse mapping, right? Under what conditions will that also be a function or a transformation, right? Again, those two words, transformation and function, are interchangeable here. All right, so it's just a very simple pictures. You've seen me drawing simple pictures like this in the past few videos if you've been following, just to show some mappings, right? Now, this time I don't have arrows because I want to go back and forth, right? We're going T, then T inverse, right? The reverse mapping. So I have a vector space U, vector space V, and let's just say that vector space U only has two vectors in it, and vector space V has only like two vectors in it, right? Just again, a very simple picture. You're not really going to come across examples like this for the most part, but just a simple picture to demonstrate a point. Now, from U to V, we'll call that mapping T, and from V to U, right, that'll be T inverse. And again, no arrows, just reverse them. So under T, you see U1 maps to V1, and U2 maps to V1 as well. And then under T inverse, V1 maps to both U1 and U2, if you reverse the mappings, the arrow, the segments there, and V2 doesn't map to anything. So do you see how in this picture the T inverse is not, by definition, a transformation, or not a function? Because again, a transformation, every element of the domain has to map to exactly one element of the codomain. So for T inverse, the domain is V and the codomain is U. Well, let's see, V1 in the domain maps to not exactly one element, it maps to two different elements. So right away I'm seeing that T inverse is not a transformation. Same thing for V2. V2 is in the domain of T inverse, but it doesn't map to anything. There's no arrows coming off of it, no segments coming off of it. So T inverse in this picture is not a transformation, since not every element of the domain of T inverse, which is V, is assigned to exactly one element of the codomain, which is U. Right. Now, here T inverse is not a transformation, as I've said. Let's look at T, right, going from U to V. If you look at T, you see T is a transformation, right? Every element of the domain, every element of U is mapped to an element of the codomain. And exactly one element, right? U1 maps to V1, and that's the only line coming off of U1. U2 has only one line coming off of it. It maps to exactly one element of the codomain, V1 as well. But T is not what they would call one-to-one, right? Because there are two different inputs, two different domain elements that go to the same range element, right? The same element of the codomain. So remember that was against the definition of one-to-one. A one-to-one transformation or a one-to-one mapping, two different inputs would map to two different outputs. That's not happening here. So T is not one-to-one, nor is it onto. Right, we're seeing that this T, if I'm going from U to V, look at T. both of these elements from U map to V1. But this element here in the codomain V, V2, this is not even mapped to. So the range is not all of V, right? The range of T is not all of V, therefore T is not onto either. So we're seeing, when T is not 1-to-1, when T is not onto, the inverse mapping, right, T inverse, will not be a transformation. And that's not good. We don't want to work with things that are not transformations because there's confusion there. Right? If I go this way, go from V to U, and I ask you, what does V1 map to? I'm confused. Do you want me to say U1 or U2? Or what does V2 map to? Well, I don't know. Nothing, I guess. Right? It's not a transformation, a proper transformation by definition, so we don't like it. We're not going to work with it. All right. So again, I'll point this out. When a transformation is not 1-to-1, when it's not onto, the inverse mapping, the reverse mapping, is not going to be a transformation. All right, we're not going to work with it. All right, let's take a look at this picture. Again, very similar. I got this similar picture here. So again, vector space U, vector space V. Say this one only has 2 vectors and this one only has 3 vectors, 3 little dots there. Like I said, not a typical example, but just an example to make a point. So from U to V is the mapping we'll call T, and from V to U is the mapping we'll call T inverse. Now look at T. T is a transformation, right? Every element of the domain of T is U, right? Every element of U is mapped to exactly one element of V, right? U1 maps to V1, and that's it. U2 maps to V2, and that's it. Now this particular T is 1-to-1, right? This particular T, it is 1-to-1, right? Because you're not getting that case where you see how different inputs are mapping to different outputs. You're not getting the case where 2 different inputs map to the same output like in the last picture. But, right, T is not onto. You see this element, again, for T, we're looking in this direction, from U to V. You see how in V here, there is an element of the codomain, this V3 down here, that is not mapped to. Right? There's no segment going to it. So the range is just, V1 and V2. The range of T is not all of V, so T is not onto. Now look at the reverse mapping. All right, let's go from V to U. Well, V1 maps to U1. V2 maps to U2. So far so good. Every element of V is mapping to exactly one element of U, so it's looking like a transformation so far. But then, uh-oh. Alright. What about V3? What does it map to under this T inverse mapping? Nothing. Right? It maps to absolutely nothing. So that does not satisfy the definition of a function or a transformation, right? One more time, a transformation. Every element of the domain set has to map to exactly one element or be assigned to exactly one element of the codomain set. And that is not happening here with this V3. So T inverse is not a transformation, not a function. All right, so we saw that when, on the previous page, when T was neither 1-to-1 or onto, T inverse wasn't a transformation. When T is 1-to-1 but just not onto, the inverse is not a transformation. Right. How about if it's onto but not 1-to-1? So here, another picture, very similar. So again, vector space U, vector space V. Say U only has the 3 vectors in it and V only has the 2. And again, the from U to V is a mapping we'll call T, and from V to U, a mapping we'll call T inverse. All right, so let's look at T this time. T is a transformation, right? Every element of U is mapped to exactly one element of V, right? Yeah, every single element of U has only one line, exactly one line coming off of it. So T is a transformation, great. But let's take a look at it though. U1 maps to V1. U2 maps to V1 also. So I've already written, see, T is not one-to-one. T is not one-to-one, right? You got two different inputs that go to the same output. That does not happen in a one-to-one transformation or a one-to-one function. Then I got U3 mapping to V2. Okay. So it's onto, right? Do you see that T is onto, but not one-to-one? Right? It's onto because every element in the codomain is mapped to. You see, there's a line going into both of these elements here. T is onto, but T is not one-to-one. Okay, now let's look at the reverse mapping. Right, this mapping we'll call T inverse. The big question is T inverse a transformation? Is T inverse a proper function? Well, look, right away we're seeing this V1 maps to U1 and U2. So just like the first picture I showed you, this is not a proper function because of this element. It's not a proper, going this direction from V to U, going the mapping T inverse, this is not a proper transformation because this element V1 maps to two elements in U, not exactly one element. Now V2 is fine, but as soon as you find one element of the domain that doesn't map to exactly one element of the codomain, you do not have a transformation. You do not have a function. So again, T inverse is not a transformation in this case. So far we have seen when a transformation's neither one-to-one nor onto, the inverse mapping is not a transformation, not a function. We've seen that when a transformation T is not onto, the reverse is, the T inverse is not a transformation. And we've seen that when T is not one-to-one, but onto, the reverse, the inverse is not a transformation. So you might have guessed by now that the only way that the inverse mapping, the reverse mapping, the only way that's going to be a valid transformation, a valid function, is if the original transformation, if T is both one-to-one and onto, right? Let's take a look here. This is my last picture for this. So similar picture, right? So again, vector space U, vector space V. Again, let's just say this only has three vectors in it, only has three vectors in it, okay? And going from U to V is mapping T. Going from V back to U is mapping T inverse. So T is a transformation, right? Every element of U maps to exactly one element of V, right? Every element of U has exactly one line coming off of it. Now T this time is one-to-one, right? Because you see, if you take any two different inputs, they're going to different outputs, right? There are no outputs that have two lines coming into them, right? Every output has exactly one line coming into them. So T is one-to-one, right? No two different inputs are going to the same output, and it's onto as well. See how every element of V is mapped to, right? So the range of T is all of V. So this case here, this picture, the mapping T, the transformation T, is both one-to-one and onto. Now look at the reverse mapping. Look at T inverse, right, going from V to U. Is it a transformation? Yes. Every element of V, which is the domain of T inverse, every element of V is mapping to exactly one element of U. And that is by definition a transformation from V to U this time, right? So this tells me, all right, just again, these are just some small examples, but it gives me an idea and shows me the conditions under which a transformation T will have an inverse, right, a reverse mapping that's also a transformation, also a function. So, a transformation T, there's a word for this, is called invertible if the reverse mapping, if T inverse, is also a transformation. All right, so this particular T up here, this would be called an invertible transformation because its reverse, its inverse mapping, T inverse, is also a transformation, right, also a function. And do you see the conditions? Right? This only happened when my transformation T was both one-to-one and onto. All right, so that's what I have written as the next point involving invertible transformations. So a transformation T is invertible, right? T inverse will also be a transformation if and only if, both directions here, the transformation T is both one-to-one and onto. T has to be both in order for T inverse to also be a transformation, also be a valid function. All right. Okay. Now, so far, I've been talking about just any transformation, right? Any transformation is called invertible if the reverse mapping or the inverse mapping is also a transformation. Any transformation is invertible if the transformation is both one-to-one and onto. But now I want to specifically talk about linear transformations, right? So very special transformations that satisfy that additivity and homogeneity properties. Right, so my next point is about, and I know it's a lot of writing here, a lot of reading, sorry. We'll get to examples soon enough. My next point is about just linear transformations, right? A linear transformation, so say T from vector space U to V, with standard matrix A, right? And the reason I talk about only linear transformations have an associated standard matrix. A linear transformation T from U to V with standard matrix A is invertible if and only if A is invertible, right? That means matrix A inverse exists. Now what does that tell you? All right. When are matrices, when do matrices have inverses? Well, that means that, first of all, A has to be square, right? The standard matrix for the transformation has to be square. So I have the same number of rows and columns, right? Be a 3x3, 2x2, 4x4, whatever. Meaning the determinant of A is not 0, right? Or it's row equivalent to the identity matrix, right? There were lots of ways to say that a matrix was invertible, or the column vectors formed a basis for the column space, right? They were linearly independent, and also formed a basis for the column space of the matrix. Same for the row vectors, right? For the row vectors in the row space. Yeah, so now one other thing to point out. This means that this has to be square in order for it to be possibly invertible, right? Again, just because a standard matrix is square doesn't mean that it's invertible, right? You've seen plenty of square matrices, 2x2s, 3x3s, that weren't invertible before. But the only way my standard matrix is going to be square is going to be if the dimensions of the domain and codomain are the same as well, right? So the dimension of the domain has to be equal to the dimension of the codomain in order for you to be even possibly invertible, All right. Because if these two dimensions are equal, then the standard matrix will be square, and then maybe the inverse will exist and the transformation will be invertible. All right. Now, if it is invertible, right, if matrix A inverse does exist, the standard matrix for the inverse linear transformation, right, T inverse from V to U, would just be A inverse. That simple. Okay. So now, one more thing to point out before examples. Hopefully this, again, that's really something to check out here. If we're given a linear transformation and the dimensions of the range and, the dimension of the domain and codomain aren't the same, then you know immediately it's not invertible. It can't be. All right. But if they are the same, then you have to check. All right. You have to check is the standard matrix, invertible or not. All right. And then final thing to point out here. And we saw this in the very first page. Remember how I talked about on the very first page this picture, all right, this picture, where when you undergo a transformation and then its inverse, you're going right back to the vector you started from. Right? When I apply transformation t, I get to v, and then I apply transformation t inverse to that and get to u. I'm starting right back. I'm ending where I started, at vector u. So that's a composition, remember? When you plug in something to one transformation and then into another one after that, right? That's called composition. So do you see that when you compose two inverses, you end up with what's called the identity transformation, where you just send a vector right back to itself. So if I compose, t inverse with t, that would be do t first, then t inverse. You'll input u and then get an output of u, right? U will map to u. And every vector in u will map to itself. And then if I composed t inverse with t and did, t with t inverse, I would do t inverse first, take this vector from v, it would map here, and then go and then apply t to it, and it would go right back to where you started from. Every vector in v under that composition would map to itself. So you'd get the identity transformation over set V there. So that's what I'm pointing out on this page. All right. So inverse transformations and composition. So suppose T, again from U to V, is an invertible linear transformation. So it's linear, and we know it's invertible as well. Now, another name for this, invertible linear transformation, right? A linear transformation that's both one-to-one and onto. Remember that was called an isomorphism, right? An isomorphism. And if there's an isomorphism between two vector spaces, those vector spaces were called isomorphic. And the only way two vector spaces could possibly be isomorphic is if they have the same dimension, as I mentioned before. So, like I said before, when you're talking about invertible linear transformations, invertible transformations, the dimension of the domain and codomain have to be the same in order for it to even be possibly remotely invertible. All right, so suppose we're given this t, which is an isomorphism, an invertible linear transformation. Then, t inverse, which would go from v to u, exists, right, is also a transformation. And you could compose them in both orders. T composed with t inverse, right, so this means I go through t inverse first and then through t, so I'd be going from v to v, right? This would be the identity mapping, the identity transformation from v to v. It would take every vector from v and assign it to itself. So this t composed with t inverse of v would be equal to v for all v in set v. Right? Every vector in v under this transformation would just map to itself. Right? Again, they call this the identity transformation over set v, over vector space v. The other way around, if I do t inverse compose with t, right, so I'm going through applying t first, then t inverse, so that would take me a vector from vector space u to u again. This would just be the identity transformation over vector space u. So it would take every vector in U and map it to itself. So T inverse composed with T of U would just be U. U would map to U. Every vector in U would map to itself under this composition. All right, and you might consider, like, you might think of this as, like, you probably saw this in an algebra class or pre-calc or whatever, but you remember, like, how they say that inverses, undo one another. So if I have T inverse composed with, T composed with T inverse of V, these like undo one another, and I'm just left with V, Same thing here, T inverse composed with T, these are inverses, so they're like they'll undo each other under composition, and I'm just left with U. But it's more proper to say that they form the identity transformation, right? The transformation that takes an input vector and it just maps it to itself. All right. Okay, and we'll check this with some examples. All right, finally, half an hour in, we're getting to some examples here. All right. So, for the next few examples, I have the following instructions. I'm asked to determine if the linear transformation is invertible. If so, then find the inverse transformation. Right, so I'll find the standard matrix for the inverse and then use it to write the rule for the inverse transformation, T inverse. All right, so this one I gave was kind of the first example here is kind of an easy one. Here I have a transformation, a linear one, right? Again, I'm pointing out that every single one of these I'm throwing out there is a linear transformation. Right. I have transformation from R2 to R3, takes this vector from R2 to this vector from R3. This one, again, very simple to determine this one. The dimension of the domain is 2, right? We've seen R2 plenty of times now, Euclidean spaces plenty of times. We know that that's 2. The dimension of R3 is 3. These are not the same, right? The dimension of the domain is not equal to the dimension of the codomain. And if that happens, all right, if the dimension of the domain is not the same as the dimension of the codomain, then right away you know that the standard matrix for that linear transformation is not going to be square, so it can't have an inverse. This transformation can't be invertible. T is not invertible, and I am done with this example, of course, not the whole video. All right, definitely not, right? And that's all I need to say. All right, so never mind writing the standard matrix for this or anything. Again, if you were to write the standard matrix for this, you would see it would be a 3x2 matrix, not square. Can't have an inverse. All right, so an easy one out the gate. All right, so now for the rest of them, I do have the domain and codomain have the same dimension, but you better check that, right? Domain and codomain have the same dimension. Right, they both have a dimension of 2. So that tells me that this might be invertible. All right, but we have to check. So T might, big emphasis on that word, might be invertible. So we have to find out. All right. All right. So it's from R2 to R2. It takes a vector with 2 components, outputs another vector with 2 components. Sorry, that's a 9 there. That's x plus 2y for the first component, 4x plus 9y, and I even wrote the word 9 there. Sorry. All right. Now, you've seen me do this before. Very easy to write, if it, especially in transformations between Euclidean spaces. Easy to write the standard matrix. So this, if it's linear, you should be able to write the output as a matrix multiplied by the input vector. So this is going to be a 2x2, right? Dimension of the codomain by the dimension of the domain for the size of the standard matrix. So it's going to be a 2x2, right? Square matrix as we want. If it's going to be invertible, it's got to have a square standard matrix, right? Multiplied by xy. And then down the first column of the standard matrix are the coefficients of the first input variable. So the coefficients of x here, 1 and 4. Down the second column, the coefficients of y, 2, then 9. All right, so I will call this A, right? This is the standard matrix for T. And I'm going to call this, like I said, I'm going to call this A. All right, so I've got A equals, this 2 by 2 matrix with entries 1, 2, 4, 9. And the question is A invertible? Because if it is, then T will be invertible. Now you can answer this a lot of ways. You can put this into reduced echelon form, and if it's row equivalent to the identity matrix, it's invertible. If all the column vectors are linearly independent and it's a square matrix, it's invertible. Well, that's easy to check. 1, 4, and 2, 9 are not scalar multiples, right? There's only 2 vectors. They're not scalar multiples, so the column vectors are linearly independent. This is and this is a square matrix, so this is invertible. Another way, though, and something I'm going to use to find the inverse is the determinant, right? The determinant of A. Now this is just a 2 by 2, so real quick, the cross minus the cross here, 9 minus 8. So the determinant of A is 1, which is not 0. All right, if the determinant is not 0, then the answer is yes. So T is invertible. If the standard matrix for a linear transformation is invertible, then the transformation itself will also be invertible. Wonderful. Now that's just part 1. Now I'm asked to find the rule, right? Write the rule for T. What is the rule for, I have the rule for T up here. What's the rule for T inverse? Again, very simple. If you have your standard matrix for A, I have my standard matrix for T. Let's go and find T inverse now. Now T inverse, T went from R2 to R2, right? So T inverse is just going to revert, be from R2 to R2 as well. We have A is the standard matrix for T. So very simply, the standard matrix for T inverse will be A inverse. All right, now for a 2 by 2, all right, you could adjoin the identity matrix 1, 0, 0, 1, and then put in reduced row echelon form, and then the right half of it will be your A inverse. You can do make the adjoint matrix and all that, but I'm going to do that. This is a simple 2 by 2. Remember, the A inverse is the reciprocal of the determinant. So 1 over 1. So just 1 multiplied by, and then that adjoint matrix where I do the cofactors, and I'm not basically these two switch. 2 by 2. This was 9, 1 here. And then you just have the opposites of these two, the upper right and upper left, the lower left-hand corners, -2 there, -4 there. And you can double check, multiply this by this, and you should get the identity matrix, the 2 by 2 identity matrix back, and you will. All right, I can see it right now. So there's the standard matrix for T inverse. Therefore, T inverse of, here's the rule for it, my input is from R2, so say xy, right? Something with two components. It could be a, b, xy, x1, x2, whatever. Should be then able to be expressed as this matrix 9, -2, -4, 1 multiplied by the input vector, right? The vector xy. And when I multiply these, I get this output, right? That's a 2 by 2 times a 2 by 1 will give me a 2 by 1. First row, first column will be 9x minus 2y. And then second row, first column will be -4x plus y. All right, and there's your rule for T inverse. All right, now let's test it out a bit, right, with some examples, right, some specific values. All right, so here we go. I got them on the same page now. So here was T, right, from R2 to R2. There's the rule for T, and then after all that work, here's T inverse and the rule for it, right, from R2 to R2 as well. Alright, so let's see if they actually are, let's just look at some examples and see if they actually are some reverse mappings. So what's T of the vector, say, 1, 2? Alright, well, if I apply T to vector 1, 2, so replace x with 1, y with 2, I get the following vector, 1 plus 4, so 5 for the first component, and then 4 plus 18, 22 for the second component. All right. And then let's compose this with T inverse. So what would T inverse of this vector be? Okay. So according to what I said before, if I do T inverse compose with T, which is kind of what I'm doing here, of any vector from R2, so I'll just say V or whatever, I should just get that vector back. All right. So T mapped 1, 2 to 5, 22. So T inverse should map 5, 22 right back to 1, 2. Well, let's see. Here's T inverse. I've written T inverse right here. I'm just going to replace x and y with 5 and 22. All right, so first component, 9 times 5 is 45, minus 2 times 22 is 44. 45 minus 44 is 1 for the first component. And then -4 times 5 is -20, plus 22 is 2 for the second component. And look, exactly what I said would happen, right? Exactly what should happen when you compose inverses. Right. Let's go the other way around. Right? Let's put something into T inverse first. Again, these are just single examples. These do not prove anything, but we're just kind of believing that these are inverses by looking at these. Right? How about T inverse of, I'm just going to go, let's say 0, 3. Right, 0, 3. So I'm going to apply T inverse to the vector 0, 3. Let's see what happens. So put in 0 for x, 3 for y. So I'd have 0 and then minus 2 times 3. That's 0 minus 6, -6 for the first component. And then -4 times 0 plus 3, I'd get 3 for the second component. Right. And then let's take this -6, 3 and plug it into T. What would be T of -6, 3? Now, if what I've done is correct, this should happen, right? So what I'm doing here is taking T and composing it with T inverse, right? Because I did T inverse first, and then I do T. Well, for any vector, that should be, this composition should map a vector to itself. So my result here should be the vector 0, 3 that I started with. All right, so let's see. Let's apply T, right? T was this up here, this rule. Let's apply T. Let's get this out of here. All right, let's apply T. Sneak up. T to the vector -6, 3. So I'm replacing x with -6, y with 3. So negative 6 plus 2 times 3, negative 6 plus 6, the first component is 0. And then 4 times negative 6 would be negative 24, plus 9 times 3 would be 27, negative 24 plus 27 would be 3. And look at that, it is the vector I started with. So after doing composition, I get basically every vector, in the domain of T inverse is mapped to itself. All right, cool. So it looked like that worked out. I found out that T was invertible. I found the inverse, and the inverse looked good. When I compose them, I end up with the vector I started with. All right, so here's another one. Again, same question. Is T invertible? All right, and if it is, find the inverse. All right, so here, and I told you that T was linear, and again, look at the dimension of the domain and codomain are the same. All right, they're both dimension 3. So this might be invertible. Do not just say, oh, the dimensions are the same, it's invertible. No, you don't know that. All right, you have to check. So now I'm told it's linear. Now, since it's linear, should be able to find a standard matrix for it. So I got this, vector with 3 components going to this vector with 3 components, and I should be able to write a 3 by 3 matrix multiplied by the input vector that would give me this same output. So again, I'll make a 3 by 3 matrix multiplied by the vector ABC multiplied by the input vector to give me this output vector. And down the first column, the coefficients of A, the first input variable, 1, 3, and 2. Down the second column, the coefficients of B, 1, negative 4, and 1. And down the third column, the coefficients of C here, negative 1, negative 3, negative 2. All right, so my standard matrix, is this 3 by 3. Again, I'll call this A. And the big question is, if I want to show that T is an invertible linear transformation, I need to show that A is an invertible matrix. So again, you could try finding the inverse or just find the determinant. But one thing I'm noticing here, look at column 1 and column 3. Column 1 is just negative 1 times column 3. Right? C1 equals negative C3. So I have a couple columns that are scalar multiples of one another. That means that the column vectors are dependent. Another thing that you would also see is that the determinant of this matrix, right, when two columns or two rows, or if you can write one column as some scalar multiple or linear combination of other columns, or if you can write one row as a scalar multiple or linear combination of other rows, you'll see that that kind of matrix has a zero determinant. So A is what they call, non-invertible, or in other words, singular. Right? A is a singular matrix, right? That means not invertible, non-invertible, however you want to put that. So this transformation here is also not invertible. If you were to reverse the mapping, it would not be a proper transformation. It would not satisfy the definition of a proper function. So T is also not invertible. T inverse is not a transformation. And that's it, right? That was all I was asked, and if it was invertible, find the inverse, but it's not. Okay. All right, so I got one more example here before I get to compositions. All right. Now this one's between two non-Euclidean vector spaces. You have the complex numbers, and then this was the set of all polynomials of degree 1 or less, right? P1. And if you recall, if you've been watching, right, whenever I'm working with non-Euclidean vector spaces, I would like to actually rewrite the transformation, All right, so here's the rule for this. It takes the complex number a plus bi, remember that I is the square root of negative 1, a and b are real, and maps it to this polynomial of degree 1 or less with 2a minus b plus 3a plus b times x, right? Some constant plus some number times x. I'd like to rewrite that transformation so that instead of, my input vector being a complex number and my output vector being a polynomial, I'm going to work with their coordinate vectors relative to the standard bases for these vector spaces. So before I get going here, let's write out the standard bases for C. I'll call E1 the standard basis for the complex numbers, which are, every complex number is written this way. So as a number times 1, right, some constant, plus a number times I. Right? So every complex number is a linear combination of these two, and these two are independent. All right, so there's your standard basis for the complex numbers. The complex numbers are dimension 2. And I'll call E2 the standard basis for P1. And it's pretty similar. Remember, every polynomial of degree 1 or less can be written as a number times 1 again, some constant, plus a number times the variable x or t or whatever the variable is. I usually use x. So 1 and x, right? Every polynomial of degree 1 or less is a linear combination of these two, and these two are independent. This is the simplest building blocks for P1, the standard basis for P1. So you see that both have dimension 2, and that's good, right? If they didn't have the same dimension, I would immediately say that the transformation was not invertible. But since they do have the same dimension, now I can keep going, and we'll check. All right. So what I'm going to do now is convert. I'm going to rewrite this transformation here into a transformation involving coordinate vectors with respect to these two standard bases. So on the left, T of, and then instead of this a plus bi, I'm going to write it in terms of its coordinates relative to the basis with the 1 and the I in it. So that is two basis vectors in it. So the coordinate vector will have 2 coordinates, and again, this is with respect to that basis E1. So I put a little E1 there. The first coordinate is just the coefficient of 1, which would be A. The second coordinate, second component, is the coefficient of I, which would be B. So there's there's the input A plus BI represented as a coordinate vector, a column vector, right, relative to basis E1. And I do the same thing for the output. Instead of writing a polynomial output, I'm going to represent this polynomial as a coordinate vector relative to basis E2, right, the bases for the polynomial set. Right? So again, there are two vectors in the standard basis, so there's going to be 2 components in my coordinate vector, and this is going to be relative to E2. So a little subscript of E2 there. Then the first component will just be the coefficient of 1, so the constant term, right? This 2a plus b, or sorry, 2a minus b. And then the second component will be the coefficient of the second vector in the basis, x, which is 3a plus b. All right, and so what I've done here is taken a transformation or a rule that takes a complex number to a polynomial, and I made it look like a transformation that takes a vector from R2 to another vector from R2. But you just have to remember that these represent coordinates and not actually vectors from R2. Right? All right, and then just like those, R2 to R2 transformations, I've already been told this is linear. You could show it's linear, show the additivity and homogeneity properties. I should be able to express this output vector now, this output coordinate vector, as a matrix multiplied by the input coordinate vector. And again, it'll be a 2 by 2, right? Dimension of the codomain by the dimension of the domain. It should be square if there's a possibility of this transformation being invertible, multiplied by the vector, AB. And again, just remember that this is coordinates, right? This isn't the actual input. I'll put a little E1 down there again, reminding me that that's a coordinate vector. Then down the first column, the coefficients of A, 2, 3. Down the second column, the coefficients of B, negative 1, 1. And there's my 2 by 2 standard matrix, right? I'll call this A, right? The standard matrix for this transformation T is that one there. Now the question now becomes, right, if I want to find out if T is invertible, is the reverse mapping also a transformation, also a function? Is A invertible? Now again, I did a nice 2 by 2 here, so it would be easy to do. I wouldn't have to go to the calculator. You see the determinant of A is 2 minus -3, so 2 plus 3 or 5, and that is not 0. So A, the standard matrix for T here, is invertible. Meaning that the transformation T is also invertible. Right. So T is invertible. All right. So now that I know that T is invertible, let's find the rule for T inverse. Now T inverse is going to take a polynomial and map it to a complex number. All right. So let's do that. Let's find T inverse. Right. Now T inverse is again going to be a mapping from P1 to the complex numbers. All right. Okay. Well, first I'm going to work with coordinate vectors. Right. So the standard matrix, again for T inverse, will simply be the standard matrix for T inverse. Right. And again, I picked a nice 2 by 2 example so I could do this relatively quickly. So remember, the inverse of a matrix is the reciprocal of the determinant. Right? So 1/5, and then multiplied by that adjoint matrix, right, which is the transpose of the cofactor matrix. I'm not getting into all that again. But basically, for a 2 by 2, you just switch the main diagonal entries, and then take the opposite of the other diagonal, the other side, so +1, -3. There you go. And if you want to multiply them all by 1/5, fine. I'll just leave it as 1/5 times 1, 1, -3, 2. So here's the standard matrix for T inverse. So I should be able to express now a rule involving coordinate vectors relative to the standard, again, the standard bases for these. All right. So remember I called for P1, the standard basis, I called that E2. And for the complex numbers, the standard basis, I call that E1. So let's just keep that in mind. So I should be able to write now that T inverse of, and again, my input is going to be a polynomial. All right, so it'll be, my input coordinate vector will be coordinates with respect to basis E2. So if I take a polynomial with coordinates, say just A, B, and these are coordinates with respect to basis E2, and if I plug them in, the output will be this standard matrix, right? 1/5 times 1, 1, -3, 2, multiplied by the AB, and this final result, right, when I actually multiply this out, and let's do this, this will be 1/5 times A plus B for the first row, first column, and then -3A plus 2B for the second row, second column. Remember, the final result, these will be coordinates of my complex numbers, right? The outputs are complex numbers, and so they'll be coordinates with respect to basis E1. All right, so I'll put the little E1 there. All right, let's, and then if you want to put the fifth in, you'd have a fifth A plus a fifth B, and then -3/5 A plus 2/5 B. That's fine. All right, I'm just going to leave the 1/5 on the outside and save it for the end. So now let's just check this out. I'm just going to check one direction. So let me go back to T. Oh, you know what? this is involving coordinate vectors. All right, so let me actually put the rule for the T inverse, right? So then I translate back to normal vectors, right? So T inverse of, remember my input here is a polynomial, so this is a plus, and I put the basis vectors in order of constant and then x term. So my input's a polynomial, so this coordinate vector here represents the polynomial a plus bx, right? And this will be equal to, 1/5 multiplied by, and then this coordinate vector represents a complex number, where the first was a constant, a plus b, plus, and then the second was the coefficient of that imaginary number I, negative 3a plus 2b times I. Right. So this is the actual rule, right? This doesn't involve coordinate vectors, right? So this is the actual inverse here, right? Because it takes polynomials to complex numbers, not just coordinate vectors to coordinate vectors, right? But they represent, this transformation with the coordinate vectors represents the same rule, though. I mean, all I did was translate back. All right, so let's test it out. All right, let's test this out. So I'm going to go back up to T. All right. T was this, transformation, linear transformation from C to P, the complex numbers, to P1 there, the polynomials of degree 1 or less. All right, so let's find T of, 2 plus 3i. All right, so I plug in a complex number to T, and according to the rule, just everywhere there's an A, I replace it with 2. Everywhere there's a B, I replace it with 3. So 2 times 2 is 4, minus 3 is 1, so 1 for the constant term. And then 3 times 2 plus 3, that's 6, plus 3 is 9. 1 plus 9x. All right, will be the output. All right, and then let's take this and put it into the inverse. T inverse of 1 plus 9x. And remember, if I did this properly, this should take me right back to 2 plus 3i. All right, so let me bring back, here is the rule for T inverse that I wrote. Right? It was right here. So this was the rule for T inverse of, a plus bx. So a is 1, b is 9. All right, a is 1, b is 9 in the T inverse here. So I get 1/5 multiplied by, and then, a plus b, 1 plus 9, so 10. And then, negative 3 plus 18, right? Negative 3 times 1 plus 2 times 9, negative 3, that's plus 15 times I. And then putting the 1/5 in there would give me 2 plus 3i. And look at that. Exactly what I started with, right? I plug 2 plus 3i into T. I plug that output into the inverse. It takes me right back to where I started. These are truly inverses. All right. And again, you can try it the other way. Plug a polynomial into T inverse, see what you get, and then take that output, put it into T, and it'll take you right back. All right. All right. Now my final example involves inverses of compositions. All right. So suppose we're given two linear transformations. All right. So say T1 from, and these are just from R2 to R2 again, just to make the matrices small and easy and all that for me. So T1 from R2 to R2 is this rule here. T2 from R2 to R2 is this rule here. And again, they're both linear transformations. All right, so the question is, find the inverse of T2 composed with T1. All right, so first let me find what is T2 composed with T1. All right. Now, if you remember how to do this, right, especially with transformations between Euclidean spaces, let's do that first. Right? Let's find T2 composed with T1. All right, now that'll be a transformation. Everything's R2 here, so it's obviously going to be a transformation between R2 and R2. All right. Now you could do this a couple ways. I'm going to do it with the standard matrix way. Remember the standard matrix for T2, T1, this is from a previous video, but I'll write this right here. Remember the standard matrix for T2 composed with T1 is A2 times A1, right, in that order. And these are the standard matrices for T2 and T1, right? So this is the standard, A2 is the standard matrix for T2, A1 is the standard matrix for T1. Right, so I'm going to go back up here. Let's look at T1 and T2 separately. Right? So T1 of vector x, y. Look at that output for T1. I can write that as a matrix, a 2 by 2 matrix with 1, 2 down the first column, coefficients of x, then coefficients of y down the second column, times x, y here, right? So this is A1, right? This is the A1 I'm talking about here, right? And then T2, do the same thing. T2 of again a vector from R2 here. Again, I can write this output from T2 as a 2 by 2 matrix with down the first column coefficients of x, 3, then 0. Then the second column coefficients of y, 0, then -1, multiplied by x, y. And there's matrix A2. Alright, so I'll do this on the next page. Let's take A2 times A1, and we'll get the standard matrix for T2 times T2 composed with T1. Right, so A2 times A1 is this A2 3 0 0 -1 multiplied by, and then this matrix here 1 3 2 4. All right, so this would be another 2 by 2 with 3 and then 9 and then -2 -4. Right. So 3 9 -2 -4. There's the standard matrix for T2 composed with T1. All right, just do usual matrix multiplication there. Okay. Now that means that T2 composed with T1 at some vector from R2, again say xy, will be equal to this matrix here, right? 3 9 -2 -4 multiplied by xy. Right? Or if you'd like to actually multiply that out, it'd be 3x plus 9y for the first component, and then -2x minus 4y for the second. Okay, so there. Now that's not the inverse, right? I was asked to find the inverse. Right. So what I want to do is find, if it exists, right? If it exists, find the inverse of this function. Right, so T2 composed with T1 inverse. All right. And this would also, everything's R2, so, T2 composed with T1 goes from R2 to R2, so obviously the inverse is also from R2 to R2, right? Just reverses that. Right? If it exists. Well, it does, right? Look at the standard matrix here. See, the determinant of this matrix is equal to -12 minus -18, right? So 6, -12 plus 18, and that's not 0. So T2 composed with T1 is invertible. Sorry about the tightness there, right? Yeah, so the standard matrix for the composition is invertible, right? So we should be able to find a rule for this. All right, now there's a couple ways you can find the standard matrix for the inverse of a composition. One is, I found the standard matrix for the composition here, and then you just find the inverse of this like I have been. All right. So I can do that right now. All right. Pretty simple. So from here, the standard matrix for T2 composed with T1 is, it'd be 1/6, right? Remember the reciprocal of the determinant of this matrix multiplied by, and then again just kind of switch the main diagonal guys in the 2 by 2s anyway, right? This is that adjoint matrix, then -9, +2. All right, so let's keep that in mind. Now another way you can find it is going back to this statement up here. Remember the standard matrix for the composition, the standard matrix for T2 composed with T1 is A2 times A1. So that means that the standard matrix for T2 composed with T1 inverse, right, is just the inverse of the standard matrix that we for T2 composed with T1. Right? So A2 times A1 inverse. Now hopefully you recall, right? And I'll put this off to the side. This has probably been a while, but recall that the inverse of a product of two matrices is the product of their inverses in reverse order. So that's what we're going to do here. Right? A2, the inverse of A2 times A1 is A1 inverse times A2 inverse. All right, so let me do this on the next page and see if we come up with the same thing I got here. All right, see if we come up with the same thing I got here. All right, so what was A1? Right, A1 was this guy, A2 was this guy here. Right? So what's A1 inverse? Now the determinant of A1, I'll just say out loud, the determinant of A1 is 4 minus 6, so -2, meaning A1 inverse starts off with -1/2 times, and then the matrix 4 with the 4 and the 1 switched, and then -3, -2. Right? And then A2 inverse, right, this was A2, the standard matrix for T2. The determinant is -3, so -1/3 times the matrix with -1 and 3 switched, and then the opposites of zeros are still zeros. Okay. So again, A2 times A1 inverse will be equal to A1 inverse times A2 inverse. Well, if I multiply both of these, you see the scalars outside, -1/2 times -1/3, that's +1/6. And then I'll multiply the 2 by 2s, 4, -3, in the order of A1, A2 here. A1 inverse, A2 inverse, -2, 1, multiplied by -1, 0, 0, 3. Right? And again, this 1/6 was just by simply multiplying the scalars. Remember, you can move scalars around in matrix multiplication. So that's 1/6. So I'm getting 1/6 times, and then you have a 2 by 2 times a 2 by 2. Will give me another 2 by 2. First row, first column will be -4. First row, second column will be -9. Second row, first column will be 2. And then second row, second column will be 3. And there's the standard matrix. And again, you can put the 1/6 in if you want. But there's the standard matrix for T2 composed with T1 inverse. And isn't that, look at that, that's exactly the same as I got earlier, right? When I took the standard matrix for T2 composed with T1 and then found the inverse. Right? So what I'm seeing here, right? So what you're seeing here is that the standard matrix for T2 composed with T1 inverse is just the standard matrix for T1 inverse times the standard matrix for T2 inverse. So this means, and I'll probably put this all on a single page later, but this means that T2 composed with T1 inverse is the same rule, is going to give me the same rule as T1 inverse composed with T2 inverse. right? Because the standard matrix for this on the left, the standard matrix for this is the standard matrix for this times the standard matrix for that, right? A1 inverse times A2 inverse. All right. That's also a big result. All right. So I guess finally we can say the final result here. So then T2 composed with T1 inverse at some input, xy will be equal to this matrix 1, 6 times the matrix -4, -9, 2, 3 multiplied by the input. Right. And if you'd like to actually multiply that out, be my guest. Right. Okay. All right, so again, big key here. All right. Not going to really plug in inputs, so those should be proper inverses. But the big key to take away from this last example is the following. So one point is, the standard matrix of the inverse of a composition. All right, so T2 composed with T1 inverse is equal to, or is, I should say just is, A1 inverse times A2 inverse, where A1 is the standard matrix of T1, right, and A2 is the standard matrix of T2. All right, and then of course A1 inverse would then be the standard matrix of T1 inverse, if T1 inverse exists. All right. Well, of course it does, because you have A1 has an inverse. And A2 inverse would be the standard matrix of T2 inverse. So this implies, again, to me that T2 composed with T1 inverse is equal to T1 inverse composed with T2 inverse, again, if these exist, right? Right, if these exist. If they don't exist, then you have to find it some other way. Like you can have invertible compositions where the two transformations themselves are not invertible. Like I could have I could have T1 going from R2 to R3 for, let's say, and then T2 going from R3 to R2. Right, R2 to R3, R3 to R2. Then you see that T2 composed with T1 would be a function or a transformation from R2 to R2. And then T1 composed with T2, that would be a function from R3 to R3. So do you see how there might be some scenarios where these could have an inverse? Right, these could be invertible because the domain and codomain have the same dimensions, R2, R2, R3, R3. But the functions themselves, the individual pieces, the ones that made up the composition, won't have an inverse at all. They can't. Right, because their domains and codomains have different dimensions, right? 2, 3, 3, 2. So, like I said, this rule that I'm writing here isn't always true. It's true if these are, if T1 and T2 are invertible, this is true. But if they're not invertible, it could still be true. All right, I'm sorry, if they're not invertible, it's not going to be true. But what I'm saying is, if they're not invertible, this might still exist. T2 composed with T1 inverse, or T1 composed with T2 inverse. All right, so just because T1 and T2 are not invertible, that doesn't mean that the compositions might not. That doesn't mean the compositions won't be invertible. Right? The compositions might be invertible, even though the original functions aren't. Right? I don't know if that made sense at all, but just all I'm saying is just be careful when you're trying to find the inverse of a composition. Right? There's a little bit much to it. But if you know how to find the standard matrix, if T1 and T2, if the two transformations that make up the composition are invertible and they're linear, should be pretty simple, right? You just find the standard matrices and find the inverses of those standard matrices and multiply them in the correct order, and then you'll have the standard matrix for the inverse of the composition, and then you could write a rule for the inverse. All right, just like those first a couple examples I did as well. All right, so a lot to end with there, right? Kind of a lot to think about with compositions. Just hopefully you enjoy practicing those, and again, you're only going to get really good at these things by practicing a lot of them. So, use your text, find other texts out there, problems online. Just keep it up. Hopefully you enjoy practicing problems like this and getting better at this stuff. Right? It's the only way to do it. And thank you very much for watching.